PC-SAFT sensitivity analysis is almost the same as before. Select parameters and run. The software then displays the sensitivity result table and chart. The experimental fitting stage is also similar. Select adjustable parameters. Run the fit and view the fitting process and final result. The other thermodynamic models follow the PR-EOS workflow with different input parameters. After 2 model calculations, add multiple model results for comparison. Select the comparison method, then compare EOS differences for a target value. Here, PR-EOS and PC-SAFT are compared for the oil Z factor result. For asphaltene precipitation, the software provides Flory-Huggins and solid model methods. Commercial tools such as CMG WinProp commonly use the solid model. The FH method is popular in literature, but is rarely integrated into software. This platform combines multiple models for broader application conditions. In the FH method, select the target asphaltene component and run the method. The output includes fugacity coefficients, FH parameters, and phase analysis results. It also shows precipitation results. Pressure scanning can be configured with range and step size. Then the curve of asphaltene amount versus pressure and the data table can be reviewed. The precipitation model also includes sensitivity analysis and experimental fitting. Select parameters for sensitivity analysis. In fitting, imported experimental data are used to tune parameters and match the target curve. The solid model is the model commonly used in commercial software. Unlike FH, it requires extra model parameters, including reference fugacity and component molar inputs. It also uses solid model parameters with a target asphaltene component and reference component. For interaction coefficients, users specify where each coefficient is applied. Pressure scanning matches FH. Set the scan range to calculate precipitation versus pressure. The reproduced solid model result is close to CMG WinProp. However, the FH calculation still shows larger error. For solid model sensitivity analysis, this module adjusts solid phase model parameters. Compared with FH, it can tune additional solid model parameters. Here, the solid molar volume parameter is selected, with upper and lower ranges for sensitivity analysis. By observing parameter changes and curve shapes, users judge each parameter's effect. Solid model fitting follows the same logic as FH. Select the target parameter, set the range, and run fitting by adjusting that parameter. This matches the result curve. The precipitation model quantifies precipitated amount under different temperature and pressure conditions. Although quantitative, it requires complex parameter input, so simple screening methods are also provided. The software includes the debore method, the index method, and chart-based methods. In debore prediction, users enter parameters to calculate a risk level shown on the debore chart. This quickly evaluates precipitation risk. Literature-based default boundaries are provided and can be customized. Changing the boundaries affects the target evaluation and supports sensitivity analysis. The method evaluates results under different conditions. The index method also uses literature-based default boundaries and a calculation formula. It then gives the precipitation risk level. In sensitivity analysis, only SARA composition information is used, with the total fixed at 100%. Choose a fixed balancing component. The other three components are varied during sensitivity analysis. Because this is an index method, the chart directly plots boundaries and point values. The chart method also uses SARA composition and two charts for rapid risk screening. The risk assessment section quickly visualizes asphaltene precipitation risk across production stages. Under surface conditions, adjust temperature and pressure ranges after surface degassing. The result shows precipitated amount as conditions change, helping assess separator risk. It evaluates choke valve blockage risk. Next is the wellbore module. In the wellbore, temperature and pressure change together with depth. This module predicts asphaltene precipitation along the wellbore pressure-temperature path. It identifies blockage risk intervals and shows where precipitation begins. It also shows where precipitation is most severe, supporting wellbore blockage prevention. Unlike surface and wellbore modules, the reservoir module considers pore-scale effects. It includes capillary effects on asphaltene phase behavior and formation damage risk. Visualization shows precipitation risk under different pressures and pore sizes. In this test case, the risk changes with pressure and pore radius. Next, AI algorithms support fast prediction and feature recognition for asphaltene behavior. The goal is efficient trend evaluation under complex conditions with less thermodynamic computation. It also aims to identify key feature points automatically using experimental and model data. Training inputs include pressure, temperature, scan ranges, and SARA or other fluid properties. Trained machine learning models predict precipitation amount and phase behavior. They output pressure precipitation curves, but this module is not fully developed yet. The previous modules assess risk. The software also provides treatment methods after precipitation. Methods include wireline operations, coiled tubing, and chemical cleaning. This area will keep expanding. The module helps engineers choose suitable interventions under complex conditions. It reduces blockage risk and improves job success. In chemicals, toluene content can be evaluated. The report export stage records software operations and selected module content. It automatically generates report files in PDF, Excel, Word, and PowerPoint formats. Users can preview the report before export. They can also right-click to open it separately. The report contains selected charts and tables. Results are described automatically. Users may import a custom template from the menu bar. The report header now follows the imported template and will be applied during export. When the preview meets requirements, export and save the report as a PDF.
Thank you for watching. This concludes the demonstration. We appreciate your time, and we hope this overview was helpful. See you next time.